a CXMT DDR5 module pulled from a desktop system sold into the Chinese domestic market in 2024 cites on the examination tray. The label reads domestic. The spec sheet claims DDR5-4800. The question the teardown is designed to answer is whether the silicon underneath those words matches them, or whether the geometry of the die tells a different story than the surface layer suggests. It tells a different one. Cut deep enough into this specific module, and the restriction intended to hold it at a certain tier turns out not to be external context surrounding the object. It is visible structure within it, readable in proportions rather than prose. The cuts run in order: packaging and substrate first, then die markings and process node, then cell architecture and array geometry, then interconnect topology, and finally the peripheral circuit proportions at the deepest layer, where the constraint stops being a policy document and becomes a dimension on the die. The first thing the teardown establishes is that this module fits the slot. That is not a trivial finding. DDR5 is a JEDEC-defined standard, specifying 288 pins, defined signal timings, and a particular voltage rail, and meeting it requires access to the specification, the tooling to validate against it, and a supply chain capable of building to it at yield. CXMT has all three. The printed circuit board under the label is clean, the silk screening is orderly, and the part number corresponds to DDR5-4800, which is the lower end of the DDR5 speed range but squarely within the standard's defined bins. Changxin Memory Technologies, headquartered in Hefei, Anhui, is the label's name manufacturer, and that name carries its own layer of information. This is a company that did not exist as a meaningful DRAM producer a decade ago, and the module in hand is the physical evidence of how much ground has been covered since. The label is the last layer that uses human language. The layers below use geometry. Beneath the printed circuit board and the label stock, the first physical layer the decapsulation exposes is the substrate, the organic interposer that routes signals from the die's bond pads down to the module's 288 pins and outward to whatever motherboard accepts the connector. In the cross-section images that have circulated from teardowns of this product family, the substrate shows a multi-layer stack with via structures that are well within the capability of China's domestic advanced packaging supply chain. That supply chain exists in its current form partly because substrate materials and via drilling equipment were among the earlier targets of Western export controls, which forced domestic development of the tooling for via drilling, plating, and lamination. The module in hand is therefore assembled on a substrate that was itself built by an industry that previous rounds of restriction inadvertently accelerated. The substrate layer count and via pitch visible in teardown cross-sections of this module stop short of what Micron's comparable DDR5 modules show in their own published teardown images. But the gap is not catastrophic, it is measurable. That measurability is itself a finding. CXMT's packaging capability is catching up along a visible gradient, and that gradient has a slope that is not yet flat. The packaging layer is not where the constraints show most clearly. That comes with the next cut inward, but it is worth noting that the outer layer is already a product of prior restriction, deposited onto a substrate that prior restriction shaped. When the die surface is exposed and the markings are read, the most important number is not the speed bin on the label above. It is the process node designation stamped into the die itself. CXMT has stated publicly that its DDR5 production uses a 17 nanometer class process. In the DRAM industry, a node number of this type is a pitch equivalent metric, not a transistor gate length, and it does not map directly to the node names used by logic foundries. What it does map to, when cross-referenced against published die size and capacity figures estimated by independent hardware analysts, is a structural tier that the leading DRAM manufacturers passed through roughly a decade ago and have since left behind. Micron's current DDR5 production sites at a tighter pitch on a node that requires extreme ultraviolet lithography to pattern its most critical layers. CXMT's process does not use extreme ultraviolet lithography because CXMT cannot obtain the systems required to perform it. ASML, which manufactures every commercial extreme ultraviolet scanner that exists anywhere in the world, has been prohibited from shipping those tools to China. The 17 nanometer designation on the die marking is therefore not just a number describing a process. It is a coordinate on a map whose boundary is drawn by the export control. The die says 17 nanometers. The process behind that designation says immersion multi-patterning. The gap between those two statements is where the restriction has taken up residence inside the silicon. The cell architecture layer is where DRAM physics and available tooling meet, and this is the layer where the dissection becomes most instructive. The cell visible in cross-section imaging of the CXMT DDR5 product family is a buried wordline architecture, the same fundamental design used by every leading DRAM manufacturer at sub-20 nanometer nodes because the physics of the cell leaves no alternative. Below a certain cell pitch, the raised wordline that characterized earlier DRAM generations couples too strongly to adjacent cells, degrades charge retention, and introduces read errors that cannot be managed by refresh rate alone. The buried wordline solves that problem by routing the gate conductor below the active silicon surface, which reduces capacitive coupling at the cost of additional patterning steps and tighter dimensional control requirements. CXMT's adoption of this architecture is not noteworthy in itself. The industry converged on buried wordlines years ago, and any manufacturer attempting sub-20 nanometer DRAM would arrive at the same structural solution. What is noteworthy is the patterning discipline required to achieve it without the tool that the industry's leading manufacturers were using to define those buried wordline layers at their own most advanced nodes. Each layer in this die that would benefit from extreme ultraviolet lithography's single exposure precision must instead be defined by 2 or more immersion exposures, with their combined edge placement errors stacking against the tolerance budget of the cell. The cell architecture is correct. The patterning path to achieve it is longer. Each step in that path adds a small yield risk and a measurable cycle time cost, and the dimensional tolerances the design must accommodate are wider than they would be if the scanner had been available. The spec sheet gives a number. The cross-section gives a shape. The shape and the number are not contradictory, but they are not the same statement. A single memory cell in this module began as a region of silicon on a wafer in Hefei, defined by a sequence of photolithographic exposures, etch steps, deposition cycles, and implant passes that collectively determine the cell's electrical behavior. The wordline trench was patterned by immersion lithography, using multiple exposures to achieve the pitch target. The storage capacitor was grown upward from that trench floor in a cylinder stack geometry, adding height to maintain the charge storage volume as the lateral dimensions of the cell were pushed inward. The bit line was deposited and patterned above, connecting this cell to the sense amplifier that will eventually decide whether it holds a 1 or a 0. The peripheral circuits surrounding the array were patterned on the same wafer, with their transistors defined by the same tools at their respective dimensional limits. The finished die was diced from the wafer, attached to the domestic substrate, wire bonded or flip chip connected to the routing layers, encapsulated, and placed on the printed circuit board that now carries the DDR5-4800 label. That label is the last transformation the cell undergoes before it enters a desktop system and begins storing data. Every step from silicon to slot was executed by a supply chain operating under the tooling constraints the restriction imposed, and those constraints are present in the finished cell's dimensions as surely as the chemistry of the deposition cycles. The metal interconnect layers above the cell array carry signals from the storage cells to the sense amplifiers, from the sense amplifiers to the row and column decoders, and from those decoders to the input/output circuits that ultimately drive the 288-pin interface. The wire pitch on those interconnect layers is set by the same lithographic tools that pattern the cell, and the figures CXMT has disclosed publicly are consistent with the 17 nanometer class node description. What the interconnect layer exposes, when examined against the DDR5 specification, is a boundary condition. The JEDEC DDR5 standard defines electrical requirements, timing margins, voltage levels, and signal integrity parameters that can be met across a range of process nodes. The standard was written to be manufacturable at the leading edge, but it was not written to require it. CXMT's process node places this die's input/output circuitry comfortably within the standard's electrical envelope. The die meets DDR5. It meets it at the standard's lower speed bins. At the dimensional tier, its available tooling permits, but it meets it in the sense that matters commercially. It fits the slot, it trains to the controller, and it serves the workload. The interconnect layer is the last layer that reports that the object is conformant. The layer below it reports something more specific. The deepest cut is the one that requires the most careful looking, because what it reveals is not a defect. It is a proportion. In the die photographs that have been published for the CXMT DDR5 product family, and in comparable published die photographs of Micron's DDR5 products at the same capacity point, the visible ratio between the memory array, the regular repeating grid that occupies the central bulk of the die, and the peripheral circuits at the die's edges is not the same. The peripheral region on the CXMT die, as the teardown suggests from visual inspection, occupies a meaningfully larger share of total die area than the peripheral region on the Micron die at the same capacity. This is the anatomist's own reading of the comparative images. It has not been confirmed by a qualified laboratory's metrology, and that distinction matters and will be returned to shortly. But the principle behind what the images suggest is not in dispute, and it is worth stating precisely. Every transistor in the peripheral circuit, every row decoder, every sense amplifier, every refresh control unit must be a certain size, and that size is set by the process node at which the peripheral layers were patterned. At a tighter node, those transistors shrink, the peripheral region compresses relative to the array, and a larger fraction of the total die area becomes pure storage. At the node tier this die occupies, those transistors are larger, the peripheral region is wider, and a smaller fraction of the die is array. Less array per die means more die area per gigabit stored. More die area per gigabit means either a larger die for the same capacity or fewer gigabits per wafer at the same die size, or some combination of both. This is not a subtle efficiency difference at the margins. It is a direct geometric per wafer cost premium that every module in this product family carries because of the node tier the available tooling could reach. Consider a craftsman tiling a floor to a fixed and correct pattern using tiles that are 10% larger than the specification calls for. The pattern is right, the installation is competent, the floor is usable, but the room that floor fills is larger than it needed to be, or the same room holds fewer complete pattern units than a floor tiled to specification would contain. The tile size is not the craftsman's error. It is the upstream supply constraint made visible in the finished floor. The peripheral region on this die is that floor, correctly laid, correctly functional, wider than the restriction allowed it to be otherwise. The peripheral to array ratio is not a design error. It is the restriction, rendered as a proportion in silicon, readable in a die photograph by anyone who knows where the array ends and the peripheral logic begins. The teardown cannot settle three things, and stating them plainly is part of the dissection. The first is yield. Die photographs reveal architecture and proportion, but they do not show how many dies per wafer meet the DDR5-4800 specification, how many are binned down to slower speed grades, and how many are discarded before packaging. CXMT has not published yield figures, and no independent analysis has confirmed them. A die that is architecturally complete and geometrically consistent with its node description can still carry a yield profile that makes it commercially challenging to produce at the volumes a competitive memory market requires. Nothing in the images resolves that question. The second is endurance. DRAM retention and refresh behavior under sustained workload, the kind of real-world stress that differentiates a competitive product from one that meets specification at room temperature under light load, requires extended operational testing with instrumented platforms. No independent benchmark of this product under sustained workload has been publicly confirmed. The company's claim is that the product meets DDR5 specification. What the specification floor requires and what the market's leading products deliver are not always the same distance from that floor, and the distance between CXMT and Micron on this axis remains unresolved by published data. The third is the precision of the process node claim itself. The 17 nanometer class designation comes from CXMT's own public statements. The die photographs allow visual estimation of cell pitch and peripheral transistor size, and those estimates are consistent with the stated node tier, but they are not a substitute for a transmission electron microscope cross-section conducted at a qualified laboratory with calibrated dimensional metrology. The visual reading is plausible. It is not confirmed. Taken together, these three open questions describe the boundary of what the dissection can prove. the architecture is established. The process tier is consistent with the stated claim and the available tooling. The constraints effect on peripheral area is geometrically visible in comparative die photography. What remains outside the dissection's reach is the production reality. How many of these dies clear the specification floor, how long they hold it under real workloads, and how precisely the node claim maps to the actual dimensions in the silicon. What this module proves, taken as a complete object from its label down to its cell geometry, is that the export control on extreme ultraviolet lithography did not prevent CXMT from producing DDR5 memory. It determined the specific form that DDR5 memory took when produced without that tool. The peripheral region is wider. The node tier sits a generation behind the leading edge. The die area per gigabit is higher than it would be at the node micron occupies. These are not catastrophic deficiencies in the sense of making the product non-functional. DDR5-4800 is a real, usable product that fits real slots in real systems and serves real workloads. But the wider peripheral region, the mature node tier, and the higher die area per gigabit are the measurable signature of the restriction in the silicon, and they carry a direct commercial consequence in the form of a per-wafer cost structure that the leading-edge manufacturers do not share. CXMT is building the capability to close that gap through process development on the 17 nanometer class node and, according to public statements, through work on a tighter subsequent node, both of which are underway using immersion multi-patterning pushed as far as the technique can be taken. The gap's current size is what the teardown shows. Its future size is what the teardown cannot predict, because the teardown only opens what is already on the tray. The restrictions set the dimensions. The dimensions are in the die. The die is in the slot, and it is running. That is what one CXMT DDR5 module shows when opened layer by layer. The question for the next dissection is yours. Which object should go on the table? A domestic Chinese graphics processor die, a Huawei Kirin processor, or something further down the stack in the memory hierarchy? Leave the answer in the comments and we will open whichever one the material supports most fully. If this kind of layer-by-layer examination is what you come here for, subscribe and turn on notifications. Every object we open goes this deep and the next one is already on the tray.